Okay, this P5 video is for combining resistors. So what you need to be able to do is to take a combination of several different resistors and basically work out what single resistor we could replace them with. And there's a couple of rules for doing this, and you need to be able to apply them in a variety of situations. So what we've got here then is a combination of a 5, 2 and 3 ohm resistor in series. It's series because there's only one path for the current to flow through this set of resistors. So the rule here is very simple. All we do is add up the resistances we've got. So 5 plus 2 plus 3 gives us a total of 10 ohms. And the way to think about what we can do then is, if we had these resistors in that combination in a full circuit, we could replace those 3 resistors with a single 10 ohm resistor, and the circuit should work the same way. So we've replaced the 5, 2 and 3 in series with the 10. Okay, so that's the first rule. The second rule is for parallel combinations, and you are only required to be able to work out parallel combinations of identical resistors, so where all the resistors in the combination are the same. And this combination is parallel because the wires branch here and we have multiple different routes for the current to take through the resistor combination. Okay, the rule here is that all we need to do is to take the value of one of those resistors and divide it by the number in the combination. So obviously they're all the same, it doesn't matter which one you pick. So we've got 3 resistors in the combination, each one is 12. We do 12 divided by the 3 in the combination to give us 4 ohms resistance in total. Okay, less resistance because there are more paths for the current to take. Okay, that's why it's easier for the current to flow through these 3 in parallel than an individual 12 ohm resistor on its own. And again, the idea behind this, if we wanted to, in our circuit, we could just replace those 12 ohm resistors with a single 4 ohm resistor and it would still work the same way. Okay, sometimes you might come across combinations that look more complicated, like this one here. All you have to do then is to find places where you can apply those 2 individual rules that we've talked about. So the way to do this one would be to start with at this right hand combination. So if we put this red box around that combination, it just looks like the first example we did. It's 2 resistors in series, okay, and all we have to do to work out what they would come to is to add them up. So we've got 2 plus 4 giving us 6 ohms, and that means that in this array of resistors, this combination, we can replace those 2 resistors, the 2 and the 4, with a single resistor that is a 6. And this is what you do. You work your way through the combination, reducing it down. They would never give you one that you would not be able to do by doing it this way. This is probably more complicated than you'll have to deal with as well. Okay, so we've done that one now. The next step would be to tackle these 2 identical 12 ohm resistors in parallel. And we do that. We have 2 in the array, 2 of them in parallel, so we do 12 divided by 2 to give us a 6. And again, we can just replace that combination in the red box with a 6. Okay? And now we're in a situation where the whole thing, right, looks like 2 identical resistors in parallel, so we can just apply that rule again. We've got 2 identical 6 ohm resistors, 2 of them, so we divide by 2 to give a total resistance of 3 ohms, and replace both of those with 3. So what we've done is we've gone from an original combination that was quite complicated like this, and we've said, okay, that combination is exactly the same as a single 3 ohm resistor. And that's how you do these complicated ones. There's one last thing to note that you could be asked, is that if you have non-identical resistors, so ones that are different to each other in parallel, you can't calculate the actual value of the resistance there using methods that you learn about. But we can at least place the limit on the resistance, and the useful rule here is that if you've got resistors in parallel like this, in a pure parallel combination, then the combined resistance has to be less than the smallest resistor in the combination. Okay, so in this case it's going to be less than 2. Now the reason for that is, if you imagine starting off with just the 2 ohm resistor there, no matter how big the other resistors are that you add in, any extra paths that you add in will make it easier for the current to flow through that combination. That means that starting from your original 2 ohm resistance, the extra paths will have to reduce the total resistance of the combination to less than 2. So that's just useful to bear in mind. They could give you a set of resistors like that and give you a list to pick from, and the one you would have to be the pick, there would only be one that was less than 2. That would be the one that you would have to pick. Okay, just finally then, have a go at applying those rules. You've got two examples of this rules on their own, and then one which needs a combination. Pause the video and see if you can do those, and then we'll just quickly go through the answers. Okay, so the left-hand one is just a pure series combination, so you just add these up. Okay, so 4 plus 1.5 plus 2 gives us 7.5 ohms. The middle example is pure parallel. We have 12 ohm resistors and there are 4 of them, so we do 12 divided by 4 to give us 3 ohms. And then the final combination here, which is a mixture of the two, the first thing we have to do is to tackle the two in series on the right hand side. We add those up to give 10 ohms in total, and then that gives us a combination which is a 10 in parallel with another 10, so there are effectively two 10 ohm resistors in parallel there, and 10 divided by 2 gives us 5 ohms. It's worth bearing in mind with all of this that, of course, a lot of the formulas you need are on the formula sheet, but the things you need to do to combine resistors are not on there, so you do have to learn the methods for doing that. And that's it.